In the meantime, let's do a little bit of work in our Python code to make this table a little bit more clear. Let's visualize our correlations in a way that we could put into a really snazzy report. And to do this, we're going to represent our correlations as a triangle instead of this whole table here. We don't need to show all these duplicate values. Showing all these duplicate values doesn't really add anything, and it just makes the whole thing look really, really busy. So my goal is to hide half of this table. And to accomplish this, I will create an array, which will help me filter out the values that I don't want to show and the values that I want to show. I'm going to call this filter array mask. And I'm going to set it equal to an array that's identical in size to this table of correlations, this correlation matrix that we've got up here. The module that I will use to help me do this is called NumPy. I'm going to have to add this to my notebook imports at the top in order to use it. So I'm going to say import NumPy as NP. I'm going to hit Shift Enter on this, import this module, scroll back down here, and then I'm going to use the zeros like function from the NumPy module. So we're at np dot zeros underscore like, and this function will create an array of zeros that is like whatever array is passed into this function as a parameter. In our case, that's going to be the return value from calling the correlation method on our data frame. So let's have a look at what this mask array looks like at the moment. I'm going to hit Shift Enter here, and we can see that we have an array of, well, just zeros. Now I need to make another modification. To filter on the values in the top triangle, I first need to know the indices of these cells in my array. Thankfully, there's another NumPy function that will help me find these. So I'm going to say triangle underscore indices, which is going to hold on to all the indices in the top triangle of my array. I'm going to set that equal to numpy dot triu underscore indices underscore from, and then I'm going to pass in my mask. This will retrieve the indices for the top triangle of the array. And now that I've got my indices, I can use my mask array to select just those cells and change their values. So I'm going to say mask, square brackets, and then triangle underscore indices, and set those equal to true. Let me show you what our filter looks like now. So I'm going to say mask, hit Shift Enter, and then you can see here that the top triangle in this array has the value 1, and the bottom triangle has the value 0. And that's because true is mapped to the value 1, and false is mapped to the numeric value of 0. So with this in hand, I can now move on to creating this beautiful visualization that I keep talking about. We're going to use our old friends Seaborn and matplotlib to accomplish this. The first thing I'm going to do is I'm going to set the size of our figure. So I'm going to say plt.figure, parentheses, fig size is equal to, I'm going to go 16 by 10. And then I'm going to use our Seaborn's Heatmap function to generate a heat map of our correlations. We had the Seaborn module as SNS, and then I can put a dot after it and write heat map. And then within the parentheses, I'm going to provide our correlations. So this was the value returned by calling the core method on our data frame. So I'm going to leave it like this, sns.heatmap, parentheses, data.core. And then I'm going to show our plot with plt.show. Let me hit Shift Enter to see what this looks like. Voila. Look at that. We're almost there. What we can see already is that the different colors show us the strong positive correlations have a dark red color, and the negative strong correlations have a dark blue color. Anything that's close to 0 is pale or white. So this color scheme is actually conveying quite a lot of information already, which is really, really neat on the visualization front. Now, if you're having trouble reading what it says down the sides and at the bottom of this chart, we can increase the font size of these labels with plt.xticks, parentheses, font size equals 14. And I can do the same for the y-axis with plt.yticks, parentheses, font size equals 14. Hitting Shift-Enter, we see it updated like so. So now it's a bit easier to read. Now it's time to add that mask that we created. We want to hide the correlations on this chart that are duplicates. Coming back up here, inside the heatmap method, we're going to add another argument. We're going to say mask, so the argument called mask is equal to, well, the mask that we've so painstakingly created in the cell above. So mask is equal to mask. And this might look very confusing, but this mask here refers to our variable in this cell here, and this Python code reading mask equals refers to the name of the keyword in this function. Let me hit Shift-Enter and show you what this looks like. Voila. Now we've effectively hidden half of our chart. So I'm going to modify this even further. I'm going to add the actual values of our correlations on our heat map. Because what I want to do is that I want to display these numbers here on our chart with the colors. So I'm going to say anot is equal to true and hit Shift-Enter. Now you'll see the values of the correlations being displayed in the heat map. Of course, by default, these numbers are actually really, really small and difficult to read. I don't know why, it's just how it is. So we can increase their font size with another keyword argument. So we can say anot underscore KWS is equal to, and then curly braces, quotes, size, colon, and then 14. 14 is going to be the font size of our annotations. The value of this anot underscore KWS argument is given as a dictionary. It's a Python dictionary that we're looking at here. And you can always spot Python dictionaries very, very easily with this kind of curly bracket notation and a key value pair or some key value pairs inside. The key here is the string size, and the value is 14. And these are always separated by this colon. Let me hit Shift-Enter and update the heat map now. Voila. Brilliant. Now, the only thing I find a little bit strange is why this background here is not white. Because I expected the styling to be a little bit different. I expected this to be a white background instead of this gray here. Now, if you're also seeing something a little bit unexpected, like this on the styling front, you can always set the style manually of Seaborn with sns.set_style, parentheses, and then provide the name of a style. So I'm going to go with white and hit Shift-Enter. And that line of code should force this background color here to be set to white. But, you know, the thing is, all in all, writing this Python code with the mask and with Seaborn and the heat map was kind of like the easy part, actually. The much harder part is making sense of what it is that we're actually looking at here. what is it that we can learn from this correlation matrix? So first off, you and I, we said we're going to be looking at two things, strength and direction. An example of a strong positive correlation would be something like NOx and Indus. Now this Indus feature measures the proportion of non-retail business acres per town. And this NOx feature measures the nitric oxide concentration in parts per 10 million. At least that's me reading it off the documentation on the feature descriptions. These two features have a correlation of 0.76. So the question is, does this make sense? And I think, yeah, it does. I would expect the pollution to be higher in industrial areas. The amount of industry and the amount of pollution should be positively correlated. But looking at this table a little bit more, you know what I found quite interesting? It's the correlation of tax and the industry variable. Higher tax levels are apparently associated with more industrial areas. And I actually found this quite surprising. So coming across these kind of relationships is why the correlation matrix is a useful tool for data exploration. But there are, of course, as with everything, some limitations. Looking at this heat map here, we can see that the highest correlation of all is the correlation between tax and RAD, access to radial highways. This is a positive correlation of 0.91, which seems super high. Now, remember how we looked at the documentation of this correlation function? We went up here and we hit Shift-Tab. And we learned that the default method for calculating this correlation is the Pearson method. Now, it turns out that one of the things that you have to know about this type of correlation is that it makes some assumptions about the kind of data that it's running on. This correlation calculation is actually only valid for continuous variables. And this means that it's not valid for, say, like a dummy variable, like whether a property is on the Charles River or not, because this is not a continuous variable. It's only got two values, right? 0 or 1. And looking back up here, where we've created our histogram for accessibility to radial highways, we can also see that this is not a continuous variable. This feature was an index, if you remember. And what this means is that our correlation calculation is actually not valid for the RAD feature, because RAD is not a continuous variable. Which goes to show that it's very important to know how the individual features are measured, what units they're in, and what the distribution of the data looks like for these features. Because we can only use statistical tools that are appropriate for the kind of data you're working with. Okay, so let's look at this last row down here, the row that reads price, which is our target value. On this row, you see the correlation of all the features in our model with the price, with our target. One of the things that I'm interested in looking for here is for which features we don't find a relationship. For which of the features is the correlation close to 0? The lowest correlation, of course, is with the Charles River dummy variable. But as we've just said, Chaz is a dummy variable with only values between 1 and 0, so the correlation measure is actually not appropriate. But what about the next lowest one? The next lowest one is this one called DIS. And DIS is defined as the distance from employment centers. Now, that's interesting. So DIS is not very correlated with price, but DIS is very highly correlated with the industry feature. Looking here, we see that there's a correlation of minus 0.71 between DIS and Indus. The reason I suspect this is the case is because many industrial areas are probably employment centers. So being far away from an employment center is associated with a low amount of industry. And this discovery adds something to my to-do list for the regression analysis stage. What we should probably do is we should check if our distance feature adds explanatory value to our regression model. In other words, does having both the industry feature and the distance feature included in the regression make our model better or worse? Can we get away with just having the industry feature, for example? Because the thing is, if a feature is not adding any explanatory value, it's often better to exclude it and try to run the regression without it. Because by excluding features, you might end up with a simpler model, and simplicity is usually a good thing. Okay, so where does this leave us? The correlation matrix is no silver data exploration bullet. While it may not answer all our questions, it can give us a bit more perspective. And the correlation matrix has its pros and cons. It has strengths and it has limitations, just like every other tool. Regarding the pros, we've learned something about our data. We've learned that the amount of tax and the amount of industry are correlated, and we've added something to our to-do list for later, namely that we should investigate if we really need the DIS feature in our model or not. Another pro is that we've learned that certain features with high correlations are possible sources of multicollinearity. Now, I emphasize the word possible, and this is another thing for our to-do list. High correlations don't necessarily imply this problem of multicollinearity, but we will revisit this issue during the regression analysis stage by running a formal test for this problem. Now, we're also learning a few things about some weaknesses of looking at correlations. For example, we've learned that the correlation calculations assume continuous data. This Pearson correlation calculation that we've looked at is not valid if the data is not continuous, as it is the case with our accessibility index or our Charles River dummy variable. And a second limitation that everybody likes to harp on about is that correlation does not imply causation. Just because two things move together doesn't mean that one thing causes another. In other words, everybody who drank water in 1850 is now dead. But this doesn't mean that drinking water will kill you. In fact, if you look at enough data and you look hard enough, you will find that there are all sorts of weird correlations out there. Just Google funny correlations or spurious correlations, and you'll find a bunch of great examples of completely unrelated things that move together purely by chance. And if you do this, you'll probably come across Tyler Vigen's website, who uses census data and data from the US Department of Agriculture to show that divorce rates in Maine and margarine consumption are in fact highly correlated. So the earlier chart of mine showing a zero correlation between these two things was in fact a lie. Tyler's chart shows us how it actually works. Now, another limitation of correlations is that they only check for linear relationships. And it turns out just because there's a low Pearson correlation coefficient does not mean that there is no relationship between two variables. Let me show you some examples so you can actually see what I mean. Here's some fictional data on a chart showing the x and y values. X and y have a correlation of 0.816. Now let me show you a different chart. This is some more fictional data, and the correlation between x2 and y2 is in fact also 0.816. And on this third chart here, you guessed it, the correlation is also 0.816. 0.816. And the same goes for this fourth chart here. X4 and Y4 also have a correlation of 0.816. In fact, these four graphs are very famous. They're called Hanscombe's quartet, and they're named after an English statistician who came up with them. These four graphs actually have very, very similar descriptive statistics and a very, very similar regression line. But of course, they're showing us completely different relationships. They're showing us that outliers and nonlinear relationships often only become apparent after visualizing the data. And this is what this implies. It means that it's important to look at these correlations and these descriptive statistics in conjunction with some charts. And with this in mind, we're going to be complementing our analysis of the correlation with some more graphical analysis. That way, we can discover if there's any hidden linear relationships or outliers in our data. As such, we're going to be visiting our old friend again, the scatter plot. But before we move on, I can't resist showing you this infamous comic strip from XKCD. If this is the kind of humor that appeals to you more than you'd care to admit, then I highly recommend subscribing to XKCD's RSS feed and get your dose of geeky webcomics on a regular basis. I'll see you in the next lessons. Take care.